Hey guys, welcome back. So in this video, I'm showing you guys the math behind a perceptron neural network. So let's jump right into it. So before we even start talking about the math behind it, we need to know what a perceptron neural network is, right? So let's talk about that. So a perceptron neural network is just a neural network with only one neuron. So I'm going to draw a diagram, and I'm going to explain how a perceptron neural network works, all the elements of it, and then finally we'll talk about the math behind it. Okay, so there's really three main parts to this perceptron neural network. We have our inputs, we have our neuron, and then we have our output. Okay, so and then the main things are going on in our neuron. Okay, so let's create some inputs. Okay, let's call 3 inputs. All right, and let's just classify these as inputs. Okay, so you guys can see visually. And then we have our neuron. All right, so let's actually call this neuron Z. Okay, this is probably the most important thing in this model. Obviously, everything's very important, but this is kind of where the magic happens. And now let's our last part is our output. So let's just draw our output here. Okay. So now what I'm going to do is I'm going to draw all the connections between these circles. So actually, before we do that, let's classify these inputs. So let's call these inputs x's. Okay. So we'll call this x1, x2, and then x3. Okay. And then these inputs are connected to this neuron. Okay. So by what we call weights. So we have these weights that connect these inputs to that neuron. Okay, so we call these weights. Let's call them weight 1, weight 2, and then weight 3. All right, and then finally, this neuron is our output, really. So once this neuron is done computing, it should give us a correct output. Okay, so that's a lot of information. But yeah, I think we're good. So now let's kind of talk about, what our program is doing. So where the math comes in. So basically, these inputs. How do we get these inputs? So actually, our program is not doing anything to get these inputs. These inputs are just going to be given to us. It's pretty obvious, but I just want to state it. So these we'll call real world. Okay. And how about these weights? Are these weights real world? No. So actually, we have to solve these. So how do we solve these weights? And then we have something else called a bias. So let me just write that down so you don't forget. So we have something called a bias. And this bias, I'm not going to talk too much about this, but just think of it as a number set to our neuron. Okay, so there's only one of it per neuron. It doesn't have anything to do with the connections. It's just one per a neuron or neuron layer. So you can see here's our neuron right here. Just want to put this here so we just know. We'll set the bias equal to 1, just because we don't know yet. So our bias and our weights. How do we get these biases and weights? So these biases and weights are, we first get them random. So we first pick a random number. So we just generate a random number. And then what's happening is we compare this random number to our designated output. And then it adds or subtracts in the training phase based on how far it is from the designated output for the weights. So that's that. So really what's happening is it's kind of like saying, like with the formula, it's kind of being like, we'll all just talk about it and then we'll kind of understand, but it's just putting it through the formula and trying to find add or subtract based on the designated output. And then this bias does the same. Okay? So yeah, that's that. So now we can actually move on to this Z, the math in this Z, because really these inputs we are giving. We have to, the user has to actually put them in, or we have to put them in. The program isn't finding them. The weights, we are going to, that's a part of the program. We are going to have to generate them and kind of compare them to the designated output so we can find our weights. But the main computation is done in the neuron. So let's talk about the neuron. So I'm just going to throw out a formula here for the neuron, and then let's talk about that. Okay. So this formula for this neuron, I'm just going to erase this bias for now, and then put it on top. So okay, so let's write this formula in green. Okay. So we have the sum of xi times w is this. Okay, so this is our formula. It seems kind of confusing here, so let me just break it down into what this is saying. So really, this is just x1 times w1 plus x2 times w2 plus x3 times w3 plus our bias. So that's really all this is saying. It's just wanting to get our x1 times w1. So let's just pass something in here. So let's say 1 is here. And then we'll put 2 here. And then 3 here. Okay, and we'll say our weight is 1, 2, 3. Obviously, these are just made up numbers. But yeah, so if we want to pass this through our formula, it would be 1 plus 4 plus 9 plus our bias, which is 1. So then we get 15. Okay, so that would be our neuron, or z. Okay, now what we want to do is we want to pass this 15 through what we call a normalization function. Okay, so what is a normalization function? So this normalization function just allows us to turn this 15 into a number between 1 and 0 and 1. Okay, so it just makes it easy to compute after. And makes it more complex. So there are many different normalization functions, but I use the most common is probably the sigmoid normalization function. So let's talk about that normalization function. All right. Obviously, you could use whatever you like. There's a lot of videos helping you choose what normalization function and activation functions you like. But I'm not going to start a debate on that right now. I'm just going to talk about the sigmoid right now. But just keep in mind that this is not the only one. There's many out there. And you just need to know which one to use for, or you just need to know that whatever you use, it's still going to work fine. But obviously, you guys can choose whatever you like. So, let me just write the sigmoid activation function right here. Okay, so we'll say sigmoid right here. So I'm just going to spit a formula once again, and then I'll explain. So what the sigmoid normalization function is 1 over 1 plus e to the negative z. So let's talk about this. So we have, we already solved for z, right? So, by the way, this is 15 right here. We just talked about that. So we just want to plug 15 in there. So let's just plug 15 right here. All right? And then, e to the 15th, that's like 2.2 something. E, and then 1 over 1. So obviously here when we have 1, it can't be any greater than 1. Okay, so let's kind of first talk about this in code, and then I'll explain the training process for this network. So let's bring this down, and I'm just going to erase this. Okay, So here's the code. So really, what we're going to do when we're passing this through the Sigmoid activation function is we're going to basically just create a function called Sigmoid, okay, or whatever you'd like to call it. And then, by the way, after this, I'll explain the function for this. Okay, and then inside here, what we're going to do is we're just going to say 1 divided by our first return this. Okay, return this. And we'll say 1 over 1 plus exponent of negative z. Okay, so, or negative z. So, this is how it's going to look, and this exponent you want to import numpy, just say. Okay, so that's the code, and it's pretty sloppy, but basically that's kind of an idea for the Sigmoid. Now let's talk about the how this is going to work. So I know all this is pretty basic, so we could just have it. We could just do this in some multiplication, division, and addition. But I'm just going to explain just to clarify. So for example, here what we do is we take all of these. So we just have a function maybe for z. So we'll call this z z get or something, whatever you'd like to call it. And then we want to pass x. Actually, we'll just put this here for now. We're just gonna use a different color. So what I'm gonna do is I'm just going to erase this. So how this function is gonna look is we're going to have like whatever the function name is. And inside here, we'll have our inputs and our outputs, okay? So let's say our inputs, we'll put this in a list, okay? And then we'll put our inputs. So we have 1, we have 2, and then we have 3, okay? And then we'll say our weights. Okay, we'll just say W. Let's just say I here. Actually, you know what? Write this down. Sorry. So our weights, and then these weights is 1, 2, and 3. Okay, and actually, these weights are not going to be given. So, this is just an example, but these weights actually should be a random right now. And the reason why I'm not just putting, I didn't just put it random right now, was because we actually have to go through the training process to get the weight. So we just can't have some random weight and then put it in to find z, right? We need to first, in our training, we could have a random weight, and then we could, do our training process and then get the actual weight, and then we pass in here. So that's why I'm just putting a list of the weights. So I'm just assuming that we already passed the training phase, and then we got our actual weights, okay? So just to clarify that. So that's why we have 1, 2, and 3 here. Okay, in our bias, we already found that. So we're going to say that's 1. And then we just want to solve this. So we want to say, inputs, this first one, and then times weights, and then this first one, and then, you just want to keep doing this. So we'll go like that. So basically we have, after this, let's just try a for loop like this. So you can have like a for loop here. We'll say 3, and then what you're just going to do is you're just going to say, we'll set I equal to 0 here, and then we can say inputs, we'll say A equals inputs, 0 times weights, 0, and then instead of 0 here, we'll just pass I, okay? So, and then we'll just add I. So I So that's pretty sloppy, but I just wanted to show you guys the code for this. And coming up soon, I will make a video on how to create a published Python library, like in my last video, but I'm going to show you guys actually how to create it. So we'll talk about all of these things. I'm actually going to implement in code. That's why I don't want to go in the code too much. But yeah, I think you guys have an idea of the code for this. So yeah, finally we want to pass this through our normalization function, which we already kind of talked about. And yeah, so our final type of thing for this would be it would be 1. So this would be right here, would be 1 over 1 plus e to the negative 15. Okay, so yeah, so we got this, and then our output would just be this. So yeah, I gotta get a calculator. But yeah, so that's it for this video. We kind of covered a lot about this Perceptron network. You know, there's nothing really that complex, but if you guys have any questions about this, then you guys can just feel free to email me or put it in the chat below. But once again, that's it for this video. Hope you guys enjoyed. Until next time, peace.